Hello everybody, welcome back to Mathlete's Corner. In this video, we're continuing with absolute values, level 3. So let's get right into it. So our first problem is the 2022 AIME 2 problem 6. It says let x1 be less than or equal to x2, all the way up to x100 be real numbers, such that absolute value of x1 plus absolute value of x2, all the way up to the absolute value of x100 is equal to 1, and x1 plus x2 up to x100 is equal to 0. Among all such 100 tuples of numbers, the greatest value of x76 minus x16 can achieve is m over n. Find m plus n. In this problem, we want to maximize this quantity. So in other words, we want to maximize x76 and minimize x16. So let's set x76 equal to x100. So that would mean x76, x77, x78, all the way up to x100, those are all the same. Now x16, we can set that equal to x1. So all of those will be the same. So x16 and x76 are the minimum and maximum values of all of these 100 numbers now. And that's when we'll achieve our greatest value that we're looking for. Now, what do we do with the values in between? So x17 to x75. Well, if we look at these two equations, we see that we have the sum of our 100 numbers, either their absolute values or the numbers themselves. So instead of thinking it just purely as a set of 100 numbers, we can think of it kind of as a distribution, especially since we know that the numbers are in increasing order. So the more numbers we set closer to the center, let me add a number line here. So let's say this is 0, this is 1, this is -1. As I was saying, the more numbers that we put closer to the center, the further the other numbers will be in the distribution. So we'll get more clusters on the left and right, at further extremes rather. So for this reason, we're going to say that all of the values from x17 to x75 are equal to 0. Now that we have this, we can set variables. So let's say our maximum is a and the minimum is b, and we can translate the given equations into equations in a and b. So we know that x1 plus x2 up to x100 is equal to 0. So from that we get 25a plus 16b is equal to 0. And 25a because there's 25 numbers from 76 to 100, and 16b because there's 16 numbers from 1 to 16, obviously. Now, the absolute value condition, the equation that we're given, is a little bit more tricky to handle, but we can still do it because all of the positive values will remain positive after absolute value, and the negative values will become positive. So essentially, the 25a will stay the same, but instead of plus 16b, we'll have minus 16b because the b's will become negative b's. And now we know that's equal to 1. Now we can just solve this equation. And we get 50a equals 1. And so a is 1 over 50. And instead, if we subtract the equations, we get 32b is equal to -1, and b is -1 over 32. And now we're looking for a minus b, so that's 1 over 50 plus 1 over 32, and that comes out to 82 over 50 times 32, some cancellation. It's 41 over 800 for a final answer of 841. On to the next question. Now our next question is the 2021 AIME 1 problem 8. It says find the number of integers c such that this equation has 12 distinct real solutions for x. Now, that is one hideous looking equation. We have, what, 3 sets of absolute values? And that's way too much to work with. So let's try splitting up into the positive and negative cases. So we'll end up with 20 absolute value of x minus x squared, all inside the absolute value, minus c is equal to plus or minus 21. Now we can move the c to the other side. We get this is equal to c plus or minus 21. Now we still have 2 absolute values on the left side, and we would like to get rid of at least one of them. So let's split into cases on that inner absolute value, so x. Now if x is less than or equal to 0, or if x is more than 0, if x is less than or equal to 0, we get absolute value of negative 20x minus x squared, and that's actually just the same as the absolute value of 20x plus x squared. So we're getting rid of those negative signs, making things a little bit easier for us. And if x is positive, then we get absolute value of 20x minus x squared. So it's 20x plus x squared and 20x minus x squared. And remember, this is equal to c plus or minus 21. Now, again, we have absolute values, and we can again split into our cases. So we notice that in this case, on the left side, the value inside this absolute value can be factored as x times x plus 20. So when x is less than or equal to negative 20, we get x squared plus 20x, because when x is less than or equal to negative 20, we see that the value inside the absolute values is positive. And similarly, when x is between negative 20 and 0, we see that it's the negative of that. Now we have to do the same thing with our x more than 0 case. So similarly, we'll factor it as x times 20 minus x. And here we see if 0 less than x less than or equal to 20. If x is less than 20, but it's positive, so x will be positive, 20 minus x will also be positive, and we'll just be left with the same thing. Now, if x is more than 20, then we have the negative, because 20 minus x will become negative. Now, we have 4 different functions over 4 different ranges. And obviously, this is more simpler to kind of think about, but we still don't know where to go with this. But we do notice that what we have is essentially a piecewise function. And normally when we have piecewise functions, we graph it. And I encourage you to pause the video and kind of think about how this graph was constructed and make sure it matches with our piecewise function. Now, if we go back to our original question, we want to have 12 distinct real solutions. We have to remember that this is either x plus or minus 21. Now, any horizontal line going through this graph will intersect the graph at most 6 points, such as these, not the bottom one, but the horizontal line on top. That one intersects the graph at 6 points, and that's the maximum for any horizontal line, because as we move it up, as we move this line upwards, here we'll only have 4 intersection points, and above that, only 2 intersection points. So if the maximum is 6 and we have 2 horizontal lines, then we would need both of those lines to go through 6 points. And now we can think about our values of c, because we have to remember the problem is asking the number of integer values of c. So we would like C plus 21 to maintain below 100 so that that horizontal line will intersect at 6 points. And we would want C minus 21 to be more than 0. So from here we get C is more than 21 and it is less than 79. And given this, we know that there are 79 minus 21 minus 1 equals 57 different values of C. And that's our answer. Now, before we end the series, I have listed here some tips and tricks when working on absolute value problems. And the first thing I have here is ideally we should split into the positive and negative cases, kind of like we did in that last problem. We split into the positive and negative cases, like the plus or minus 21. Then we set it to C plus or minus 21. And then we actually continue doing that for all of the inner absolute values. And the next one is something we really saw in levels 1 and 2 when we were graphing. We're looking for symmetry so that instead of dealing with, say, 4 cases, if we have an x and a y, instead of dealing with 4 cases, we can deal with 1 and just multiply by 4. And the last tip I have here is when we're working with complex numbers. We did this a lot in level 2. We can either algebra bash, so that would be using this property here. So the absolute value of a plus bi is the square root of a squared plus b squared. And if algebra bash is too complicated and too messy, then you can always resort to the complex plane and find a geometric approach to the problem. But that being said, that's all for this video. Thank you for watching. Don't forget to hit that like and subscribe button, and we'll see you next time here at Mathlete's Corner.